Rene Orlando Medrano Torricos from Unifesp. As usual, I'm going to introduce a little bit the career of the speaker. So he got his PhD in 2004 in USP. After that, he has been a postdoc for 6 years in USP. Then he moved to the Mediterranean Institute for Advanced Study in Spain. And finally, he had another postdoctoral appointment in Imperial College before coming back to Brazil, right? Right now, as we said, he's a professor in Unifesp, in the Diadema campus, here in Sao Paulo. He's also, I understand, he's related with graduate program in physics in UNESP, right? So you have also an appointment here. And his research is based on nonlinear dynamics, let's say, bifurcation, synchronization, and today's talk is going to be about that because he's going to talk about the Kuramoto model that, if I understood the single thing about synchronization, is that the Kuramoto model is super important for synchronization, right? So the title is going to be Basin of Attractions in the Kuramoto model, a linear study. Rene, the floor is yours. I think it's working.
No. Hello?
Yeah, it's
not
working.
Not working, right. Okay. I don't know. I thank you very much for the introduction and also for the invitation. It's a great pleasure to be here and present a little bit about my work. I would just ask someone if everybody speaks Portuguese. Is it okay? No?
I think that the standard is to stay with English.
In English?
Yes.
Oh, okay. Because there are some students that are probably at the internet and that they can not understand very well. But that's fine. Okay. Well, I am from the let me see here. I am from the Department of Physics at UNESP, and my students of master and PhD comes from UNESP, from Rio Claro, where I teach there, just for graduate in the graduate program. And well, this is a work based in attractions in the Kuramoto model, made by me and majorly with my friend, colleague at the Unifesp, called Antonio Mihara. Okay, so a very fast summary about this talk. I'm going to show some movies about the networks in nature. After this, I'm going to show that the Kuramoto-Sakaguchi model can explain some of these networks in nature. And then I'm going to show that this kind of model has a multi-stable. There are many equilibriums in this system. And then, so this is a study of this stability. And then we are going to try to find how these attractors are more attractive, or in other words, which one has the biggest basin of attraction of the others, right? And this is what I'm going to talk here, okay? So this is the first moves that I want to show you, and probably it is here. No. Sorry. It's absent here. It should be three movies here. There are only two. What happened? Yeah, it's this one. Mine is here. Ah, it's here. Oh, okay. So these are fireflies. This is in Thailand. Here is someone put here a LED, a green one, and starts to to do this periodic excitation. And then this is a LED, right? So this is in Thailand. And then we have a firefly here, which starts to oscillate together. So this is very interesting because they do this to reproduce. That's the thing. They try to attract the female, and then they do this periodic oscillation here. But they synchronize. You can see here somehow synchronization. And this in Thailand is very, very big. In the forest, the people can see very far from this place. So you can see here they are almost in the same period, and you can see wavelength, right? Here, also synchronized. The light starts here and goes to this direction here. Okay? Yep.
Suppose it was random and not synchronized. Would it be much more difficult to see?
You mean
for a female?
The LED? The LED random?
No. If the fireflies were not synchronized, you claim, or the people claim, that the synchronization is for reproduction.
Yeah.
Suppose it was not synchronized and they were just randomly, but with the same frequencies, just random.
I don't
you think
know.
it would be more difficult to see?
Yeah, I don't know. I don't know if they will have the same frequency, because this just happened in Thailand, in that region. These fireflies does not exist here. Here they don't do this dynamic. So here is random. If you put a LED here in the forest in Brazil, you are going to see, you are not going to see any pattern.
So why do people claim that synchronization is good for reproduction?
Well, this is the study of biologists. I don't know. Sorry. Okay. And I want to back to maybe this one. How to show full this one? Control F? Alt F? Oh, maybe. Oh, sure. It was obvious. Thank you. Okay, so this one was the first example. The other one is the Millennium Bridge in London. This was a very interesting project. This was to celebrate the millennium in 2000. And then the architect who did this, he was thinking to do something very modern. So it's like a light that goes in a line, right? So you can see the structure is supported by two wise structures here, and they are not as common. As common, you have how to say this, the structure that supports the bridge is a stick, right? And then you don't have it here, stick, right, like this. You don't have this one. It's just this one. This is in the lateral. And the idea is you can see the Thames. This is the Thames River. You can see the Thames River without anything in front of you. So that was the thing. And what happened, that was the project. And what happened here people start to walk, and they start to oscillate. Look. They start to oscillate, and they synchronize one each other. People go, look, to the right, left, walking. So this was not expected to this bridge. They tried to diminish the number of people crossing the bridge, but it doesn't work. So they have to close the bridge and solve the problem. Look. And what has happened here is that when people are walking randomly, but in sometimes you are, most of the people are in the right side and the other are in the left side. So what happened? When this very small perturbation of the system in one direction starts to oscillate the bridge. And when the bridge goes to that side, you need to put the feet in the other side, because you are going to fall. And when you do this, you push the bridge to the other side, and then start to oscillate by the people. The people is the problem. And it was also verified, and it's a very interesting. There are a lot of examples in nature where synchronization is very important. In this case, it's not good, it's bad. But yeah. So these are some examples. And this is the model that can show that this kind of waves and the synchronization can happen in this model, Kuramoto-Sakaguchi model, which is a very simple model. What is this? We have an oscillator. Here we have 12 oscillators, and theta x. This is the dynamics of each oscillator. So very simple. And then what we do is to couple the oscillator with the nearest neighbors. In this case, here is R is 4. So each one is connected with the 4 nearest neighbors on the left and on the right, right? And this is the strange coupling, and the coupling between the oscillators is given by this theta x m plus n and theta x, right? So that's the dynamical system. And this is the full connection, because all the oscillators are connected with R equal 4. They are indistinguishable, okay? We cannot differentiate one to the other. Well, and then, yes? Sorry.
So in the case of the coupling, when you go into a more distant point, that's gonna be, the coupling gonna be different, or the coupling are equal independent of the distance, or do you have this dependence?
You can do this by this guy here, Gn. So this is the coupling between x n plus n to x. This one. So for each n, you have one coupling. But what is important here is that they are symmetrical. The coupling is symmetrical. So I mean, the coupling to the 3 and 2 is the same, the 3 and 4.
Yes, but for example, in between 3 and 7, that's more like weak than 3 and 2, or is the same?
It's up to you. The
Okay.
question, the only thing is this one must be symmetric.
Okay.
That's it. Okay. Okay, so in this situation, one of the solution is all the oscillators are in the same phase. So it means that they are completely synchronized. Look, as they are indistinguishable, omega x is just a rotation addition. So we can consider 0 because all of them are rotating in the same, with the same frequency, omega x, right? So we don't need this omega x. In this case, just to be easy to understand, let's think that alpha is equal 0. When alpha is equal 0, we can see here that the equilibrium that can have here is delta equal 2 pi over n times q. And what is delta? It's the difference between these two angles. So when q is equal 0, all of they are synchronized, right? When q is equal 1, so this is the difference. You can see that the difference between this, the phase difference between these two oscillators are the same in all of them. So this is an equilibrium also. This is an equilibrium because alpha is equal 0. What you have in one side, you are going to have in the other side as the same way. Alpha is a constant Sakaguchi. It's a constant that characterizes the Sakaguchi model. But yeah, it's a delay. It's a constant that you put inside. It's a very important constant. Okay, so
you're gonna comment about the importance of this extra. Okay.
Yeah. For q equal, so this is for q equal 1. For q equal 2, you can see here the oscillator here. This is the 2 pi over 12, and q equal 2, right? This is the difference of this phase. You can see that for q equal 2, we need to distribute all the phase. You can see that from the oscillator 0 to the 6 to the half, we have 2 pi. And then from 6 to 0 again, we have 2 pi. So there are 4 pi. I need two revolutions. This is why this is called a twist state. So this is a twist state, q equal 2 and q equal 1, okay? And so on. Well, what we did here in this work, the question here is, which one of these states are stable? That's our question. The problem is that we have n states here. 2 pi over n q is from 0 to n minus 1. This is q. When q is equal n, of course, delta is equal to 2 pi, so we are in the same solution. So we have n solutions here, n stable, n equilibriums here, but which one are stable? And this is what we did in this work here. We calculated these eigenvalues. Here, until this time, everybody calculates the stability or not when the connections are full, completely connection, n goes to infinity. That's and here n is finite, and r, which is the number of coupling, are also finite and can be anyone as possible in the model. So for this solution, this is the real part of the eigenvalues, is this one, and alpha is here, cosine of alpha, and this is the imaginary part, the complex part of the eigenvalues. So we can see here, if alpha is 0 as the original Kuramoto model, we don't have the complex part. So we only have a real part, and we don't have oscillations because of this. Well, but for alpha different than 0 and pi, we have this complex part. So we have a wave function, and this wave function is something like we saw in the Fireflies movie. Yeah? This, sorry. There is a perturbation of the, we perturb the system. There is by epsilon. And then this epsilon, we can construct a matrix for this perturbation. And the Jacobian of this matrix is the eigenvalues that I'm talking here. Okay, it's about the perturbation.
Excuse me.
Yeah?
I have one question. You told before that the J don't depend of the X and Y position. When my friend asked you if the weight function J depend of position of the particle, you say that it is not dependent of the particle position.
Here, the Q.
Now the Q, the J. The
G.
Yes.
Yeah, this is a constant that can you see K here.
Yes.
Is my neighbor, is the number of my neighbor.
Okay.
When K is equal 1 is the first neighbor. K equal 2 is the second neighbor, and so on. So this one, for each K, we have one coupling. But if for K equal 1, and so here, okay, there are, it should be from minus R to R.
Yes.
Right?
Our question is to know if G1 equal to G2 equal to G3 equal to G4.
It's not necessary. It's
Okay.
not necessary.
Okay.
These only must be symmetric. Can be Gaussian.
Follow-up question, right? So, but you have this table on the left about stability, right, of different combinations of Q and R. But G is not showing up there. Do you mean that independently of these relative strengths of these Gs, it will be attractive independent of the values of G?
Okay, sorry. This what I'm showing here is for GK constant.
Oh, they are all equal.
Yeah, they're all
Okay.
in this case.
In that table,
in
they're
this
all
case,
equal.
Yeah,
Okay.
in this case, but the solution of the eigenvalues, it's not.
Is general.
Yeah,
Okay.
It's general.
Okay. Okay.
That's the connection. I think. Yeah, I see. Sorry, I didn't remember that the GK was constant here. But okay, so GK is constant. The attractive here is alpha is lesser than the model of alpha is lesser than pi over 2. And you can see here, if alpha is equal 0, the sign equals 0 or pi, the sign is equal disappear. But here the sign change. So when alpha is lesser than pi over 2, the model, this thing here, what happened is negative. So we have attractors. This is what we call that the regime is attractive. When alpha is greater than this, cosine alpha is negative. So we have this positive eigenvalue here, which is the regime is repulsive. Okay, so this one is what happened with the attractive regime, alpha in this size. But for this particular set alpha is equal to 0 for this simulation, for this one, right? Okay, so then we can analyze the stability. If all the eigenvalues are positive, we have equilibrium which is repulsive. Here is the R, is the number of connection. This one is for a network with 20 oscillators, so from 0 to 19. And R can be from 1 to 9, right? So this is the set. Then for each R, for R equal 1, it means only the first neighbor is connected, is coupled. We have attractors for Q equals 0, for Q equal 1, Q equal 2, up to Q equal 4. For Q equals 6 to 14, they are repulsive. It means that all of these eigenvalues here are positive. And we have another thing here. This is a saddle, so we have positive and negative eigenvalues. And this N here are because some of these eigenvalues are null, are 0. This is called non-hyperbolic equilibrium because one of the eigenvalues is 0.
And instead, when you write 0 means that all of them are 0?
No.
There is...
This one, yes. When R is equal 1 and the N is pi over 4, when R is equal 1, so we don't have the sum, but Q is pi N over 4, which is here. We have 20 and here is 5. N over 4, we are going to have P over 2. And cosine the P over 2 is 0, and all of them are 0. Okay, so this is what we have here. This is the stability, and this is the other solution. This is for the repulsive regime. What is going to happen here is everything that is attractive here, in the other case, will be repulsive, right? And then, yes? No, not necessarily.
Nothing to do with that?
Not necessarily.
With chimeras? Not necessarily, but okay.
Yeah.
Thank you.
I'm not going to talk about the chimera, but I have some results with the Kuramoto with chimera also. Okay, so the only different surprise that we cannot see here happens here is this kind of attractors here, which is some of the eigenvalues are null, but the rest are negative. Okay, so this is called neutrally stable. So I'm going to talk about this later. Well, so we can see here for R equal 1, we have a lot of attractors, and that's our question. For R equal low, we have many attractors, and then let's see which basin of attraction is bigger than the other. So just to introduce here this basin of attraction, everybody I think in his audience knows, but we have here an attractor.
Sorry.
Yeah.
Just maybe a short question, because the eigenvalues that you have, they are complex, right?
Yeah.
But in that, do something different, because the imaginary part, because see, in the wave function, because of that's complex, you have something like a packet, right?
Mm-hmm.
And that's introduce something, the value that the analysis that you're gonna do, that you are doing, because you can mention about that maybe.
In practical, what's going to happen here in our simulation, in these results that I'm talking about, alpha is equal 0 in this. But in general, it means the following, we are not going to have an equilibrium.
So in that case, the alpha is equal to 0, you don't have the complex part.
Yeah, in this case, for this thing. But it doesn't matter, because this is just the transient. Look, what's going to happen is this time, if all eigenvalues are negative, this term here is going to go to 0.
Yes, but...
So they are going to the equilibrium, and then what happened? The difference of the phase, they are going to lock in this different space, and they are going to oscillate together. But if you are on you are not going to move. They are always in the same distance. But there is in real, in the general laboratory, you are going to see the oscillation. But the distance between them, which I'm talking about, the equilibrium, is fixed.
Yeah, but you can have some decayment, right? Because the imaginary part or something like that.
Yeah.
So that's
but
can do
together.
Different things, right?
They go together. I mean, in all of the oscillators, it will happen as the same way. So what's important here is that the distance between them, in terms of the phase, is locked. They have movement.
Thank you.
Okay, so here initial conditions in this region here goes to infinity. Initial conditions in the yellow part goes to this attractor. This is one example of this trajectory here. But what we see here is the boundary between them is smooth. This is in general this is made because we have in the boundary we have a saddle. A saddle or equilibrium or periodic orbit here, which the stable manifold is the boundary. Is this boundary? Okay, so it's one point here. What I wanted to say here is that this attractor, the basing of attraction here, the area, does not. It's not due. The attractor is doing about this saddle here. The saddle says what is the size of this basing. That's the point, not the attractor. And here we can have something a bit complicated. There are two attractors here, but here happens the same thing, but the saddle, the stable and the unstable manifolds cross each other, and then we have a chaotic saddle which disturbs completely the boundary, and we have something like fractal. In both cases, the attractor don't give us any information about the boundary, about the basing, the size of the basing. That's the point here. So there are some different basings of attraction which are interesting. This is a WADA basing. In each boundary here, we have here 3 attractors. The basing are yellow, blue, and the gray one. And in each boundary here, you have the 3 basing here. This is the basing of the WADA basing. And this is called Rideau basing. And in this kind of basing, when you have one position in the basing of attraction of one attractor, any neighbor has also part of the basing of the other attractor. So this is Rideau. This oh.
In case of B, could we say that we have a coexistence of attractor?
Yeah.
Ah, okay.
Yeah. There is one attractor here, and the other attractor is here.
In this one, what you mean is that if I'm locally at the attractor, only looking there, I have no information there that can tell me what the border is.
Exactly.
Is that the affirmation?
Exactly.
That's special. That's not the case on every attractor.
This is in general.
Oh, this is in general.
This is in general. Not only locally. You don't have any, you can...
Well, globally, you know the whole, you know what the border is, right?
Yeah, but but not analyzing the attractor.
Okay.
You have to verify where is the saddle
Oh, okay.
that made the border, that made the border. Okay. Well, I think I don't know how is the time here.
We are quite flexible in any case, especially when there are questions.
Okay. So this one is an example of the importance of the basing. Here we have a network with there are 100 units. This is the dynamical system. It's a Duffin oscillator. This is the term of coupling. When sigma here is 0, we get the Duffin oscillator. And here, all of the initial conditions of the 100 oscillators are in the same position, Only the 50 here, this one is out of this one. So what happened here, as they are out, they push the other oscillators that it's coupled with him. And then they disturb the system, but they synchronize again. Here is the oscillators. This is the Y variable here, and you can see that all the oscillators has the same value. So in this case, and look, the space here is -3 to 7. This is huge, right? So we disturb this oscillator here, the 51, with 10 to -4. And then what happened? It does not oscillate anymore. They desynchronize completely after time, and then it stay as this way. What happened here is that in this case, when the oscillator goes, there is what's happening in this dynamical system here. We have only a periodic attractor, and we have a saddle chaotic behavior far from it, just a saddle chaotic. So if you take one node, one of these elements, and put inside the chaotic saddle, the chaotic saddle try to maintain this saddle there, this oscillator there, and it starts to push. Depending on the time that it stays there, all the other oscillator will achieve the chaotic attractor or not. And here is not, and here is all of them are going. So this is that's a work we did with Medeiros here. He's a professor now in UNESP, Rio Claro. Okay, so this is our problem, returning to our Kuramoto system. This is a very important paper of the Willie, Steven, and Strogatz, the synchronization basing. And just to remember here, we have here many attractors, and each one has the basin of attraction. So what they found this the basin size of each one obeys a tantalizing. Sorry for my English. Simple statistical law the probability that the final state has Q twist follows a Gaussian distribution. So this is one thing which was not expected. And they just measure in the simulation. And they also found that the standard deviation of this distribution grows linearly with n over q. Q here is our R. N is the number of the nodes, and Q is the coupling, the R. It follows in a line. And we have been unable to explain either of these last two results by anything beyond a hand-waving argument. That was how he finished this. This is a very cited article. And then, this is the question. Look, here, this is for R equal 1. Here we have 80, n is 80. And then there is some stables attractors. Q equal 1, Q equal 2, 2, 3, 4, 5, and so on. And they are distributed here as a Gaussian. So this is, they measure this. Another thing is the standard deviation of this Gaussian is linear. When we change R, when we change N, we are going to get to these other points here. And so there is a set of Gaussians here. And this gives us this line. This is linear. And this is, they calculated it's about 0.2 NR. So that's the two open questions that they give to us. And then with our eigenvalues, now I'm going to talk about the Kuramoto model. So now alpha is equal to 0. And then, let me show this one. What we are going to do is the following. We are going to get all the eigenvalues of the Q state. And we sum all of them. If it's attractor, it's a negative. It's a negative number. And we normalize this one with the eigenvalues omega 0, gamma 0. Why we do this? Because gamma 0 is the biggest one. It's the biggest one, so this gamma Q, capital gamma Q here, it's from 0 to 1. Okay, so this is for the attractors. And then we did the following. Okay. This is another paper where it's from the Labai, where they tried to measure the linear size of alpha t. It means it's the following. You have the attractor of the state Q equal 10. It's here. They put all the initial condition here, and randomly they start they do the initial conditions and try to verify when one of these nodes get out the state 10, which was a stable. Okay, so the size of this perturbation, they call it typical linear size. They say, after this, I am out of the basin of attraction of this attractor. Before this, small of this, we are in. And what we did is this gamma Q here, which is the sum of the eigenvalues. We plotted the same experiment that they did. This is numerical. And this is with our term here. We can see the similarity. It's very, very, very common. Well, yes?
I was wondering why these values for n, like 20 plus 3, 40 plus 3, and so on.
Oh, each one of these lines here N is equal 23 here, 43 is about this line, 83 is this one, and so on. Is this?
Why they chose these values?
Ah, okay. They just try to measure. This is what they presented, but I think they do a lot of measures.
Yeah,
it's just an example.
I agree with Sidney. It's peculiar that they almost double all the times the number, like they do 20, 40, 80, 160, but then they add a 3. So it is kind of curious why they decided to add a 3 to all of them, a 3. Like, you know, so I guess they have a good reason to add 3 to all of them, right? I mean, it's...
Yeah.
But you don't, they don't say.
I agree, I don't.
But they don't say why they,
no,
okay.
No, they don't say.
Okay, it's funny.
They said that they did some experiment, and this is the number, the experiment they did, just this. And probably. But what we did, we used the same numbers here, and we get the same scale, the same curves, right? So in some sense, the eigenvalues has the information of the linear size of the basin, in some sense, because they are very similar. So the question is, if you want to know the model, the volume, so we have to take this one power n, because the dimension of the system. So this is what we did. We put power n, and then we obtain analytically here the a Gaussian equation here, which is this line here in red. The blue one is measured, is a experiment, and the red one is this equation here, which is the first problem that Strogatz has shown. And then we try to verify the standard deviation, but we have a different equation about the result, the comparing with the result of the paper. We have that the standard deviation over n is equal to this one, right? And then this is a numerical experiment, and this is this equation here, is this line here. And we are very close, and the angle is the same. So this is very, very, very close, the result. But we can linearize this one for r very, very small. We can linearize this one and try to obtain the linear equation that the Strogatz said in his paper. Is this one. And we obtained this one. There is a term here, and here that we don't have in this case. But look, the angle, the deviation, they are the same. This is analytical, and this is the numerical approach that they have. So with these two results, we could solve this question of that these two open questions. This was published here in 2022 with Mihara and my colleagues, a PRL letter. Okay, so this is another thing about the stability of non-hyperbolic stability. So now we have the repulsive regime, and we are going to study this kind of attractor here. Here, we are going to focus in n equal 8, r equal 8, and r equal 9, but for q equal 3. We have this one and this one. Oh, sorry, let me see here. It's r equal 8, r equal 9. Well, I think it's this one. It's this one. This is, yeah, it's Q equal 5. So in Q equal 5, we have R equal 8, R equal 9, and then we calculate the eigenvalues for R equal 8. We can see is this red one. You can see that all of them are negative. So R equal 8, this state here, is stable. It's stable. And for R equal 9, there are a lot of eigenvalues that are null. The others are negative, but there are a lot of that are null. So what happened with the dynamics? We have here an initial condition, which is a random initial condition. For this situation, R equal 8, all this initial condition goes to this distribution, which the distance is the same. So this is an equilibrium state. For R equal 9, this initial condition goes to this distribution, which is not more symmetric. We don't have more symmetry, which is something strange because all the nodes are indistinguishable. They are equal. And all the force of the other nodes are the same for one node. But we get this one. And what happened here is exactly this one. Because we have the eigenvalues equal 0, imagine we have we have this position here that the eigenvalues, this is an eigenvector where the eigenvalues is 0, and there is another one here which is negative, which is the case of here, 0 and negative. So initial conditions randomly is because of the stable eigenvalues, it's going to this direction and then goes to this state where all the eigenvalues are null, and then it stops there. This is why we don't have a symmetric or homogeneous distribution of the nodes. Okay, so this is our last result. We are working on this one. This is to be published. And thank you very much. So.
Thank you very much. We already had a few questions, and we have already one that is going to start.
Thanks for the talk. Suppose it's not periodic. So I don't want to take n to infinity and leave it periodic. Suppose you cut the link. So that n equals 0, n equals 1 has no connection with any of the other, with the last n. So I don't want to have periodic boundary conditions. A Firefly does not have periodic boundary conditions.
Yeah.
So how does that affect the analysis?
Yeah, okay. We didn't do this one, but probably we are not going to achieve the solution of this eigenvalues.
So how is this related to Firefly? So are the main properties of this connected to the fact that it's periodic?
Yeah.
So how is that
you
related
mean
to Firefly?
it's a ring?
Yeah.
Yeah. That's the
So how do you connect it to Fireflies then?
No connected. I'm just saying that this result here has the wave function.
Okay.
So that's it.
Okay, thanks.
Yeah,
Some more? Yeah. No.
Okay, I want to know if we, in the last presentation, the last page, yes, if you change the size of the system, like we take n equal to 200, the dynamical system will change, the configuration of dynamics system will change?
Yeah, what's going to have here is that this configuration we are not going to have here for Q equal 5. It will change. But this solution, attractive and neutrally attractive, we are going to have.
Okay.
Always.
Some more? Okay. If not, we can thank our speaker again.
Thank you very much.